Okay, 2.2, square root of a function. So let's take this a step further, thinking about square roots of a function. We will graph. What's going on? Graph just a regular old y equals f of x function, and then we take the square root of the function, and let's look at some of the patterns and the behaviors of what happens when we take the square root of a function. So to graph y equals square root of f of x, let's set up a table of values for the graph of f of x, then take the square root of the elements of just the range while keeping the elements of the domain same. So mapping wise, this is what we're doing. The invariant point. So invariant points means these are points that stay the same whether you're on the base function f of x or the square root of f of x. These are points of the graph of square root of f of x that are the same as the points for f of x. And these invariant points are located at x0 and x1. So where y equals 0 and y equals 1 are where my invariant points lie. Relative locations of f of x and y equals square root of f of x. So this is important when we do graph sketching. You cannot take the square root of a negative number because the Cartesian coordinate system we're working in are real numbers. If you take the square root of a negative number, you'll get complex or imaginary numbers, and we don't deal with that in this course, okay? So the domain, for the purposes of this course and this lesson, the domain of y equals square root of f of x is any value for which f of x is greater than or equal to 0. The range is the square root of any value in y equals f of x for which y equals square root of f of x is defined. The graph of y equals square root of f of x exists only where f of x is greater than or equal to 0. You can predict the location of the square root of the function relative to f of y equals f of x using the values of f of x. So let's think about it this way. First case, f of x is less than 0. For the square root of the function, this is undefined because you cannot take the square root of a negative number. When f of x equals 0, the graphs of f of x, square root of f of x, and f of x intersect at y equals 0. This is an invariant point. The graph, next one, f of x is greater than 0 but less than 1. The graph of the square root of f of x is above the graph of y equals f of x. I'll show you this one with an example. This one, you got to be careful when you think about this. F of x equals 1. The graphs of y equals f of x and y equals f of x intersect at y equals 1. This is also an invariant point, along with y equals 0 and y equals 1 are two invariant points. When f of x is greater than 1, the graph of y equals f of x is below the graph of y equals f of x. So if I do a chart here, let me just do another page here. And if I set up let's do x here and y equals f of x and y equals square root of f of x. And let's look at the various regions here. So if I have -2, -1, these are values where f of x is less than 0. So let's do this. I'm going to say y equals x, y equals square root of x. Let's use actual values here, or actual functions. So y is just -2. Y is -1. This one, because y equals square root of -2, well, that's undefined, so undefined. Same thing with -1, undefined. All right, so that's that one. Let's keep going. The next one is when f of x equals 0. This is a special case. When x is 0, my y value is also 0. When x is 0 for the square root, y is also equal to 0 because I have y equals square root of 0, and that's 0. All right? So this is my first invariant point. Let's keep going down. When f of x is between 0 and 1, but doesn't equal 0, doesn't equal 1. Let's say x equals 0.36. I'm going to pick nice, like perfect square numbers just to illustrate. Okay, so this one, got to be careful with decimals. You can take out your calculator and try this. For y equals x, well, y is just 0.36. What happens when y equals the square root of 0.36? And remember, we only want positive values, right? All right, so I do square root of 0.36. Well, that's 0.6. Let's do another one, 0.64. Well, y just equals 0.64. But when I take the square root, this is 0.6. When I take the square root of 0.64, I get 0.8. Let's do one more, 0.81. Well, the y value here is just 0.81, but when I take the square root of 0.81, I get 0.9. Okay, so you see the pattern here. Oops, sorry folks. So let's make a statement here. This is that region where f of x is greater than 0, but less than 1. And what happens here is square root of f of x is, the graph of y equals square root of f of x is above y equals f of x. And you can see that with these y values. You can see that this y value 0.8 is greater than 0.64, 0.6 is greater than 0.36. Okay, next set here. F of x equals 1. So when x equals 1, y equals 1. Well, y equals square root of 1, that's just 1, so y also equals 1 for the square root of the function. This is another special case where f of x equals 1, and this is our other invariant point. And let's do our final case here. F of x is greater than 1. Let's pick one that's not a perfect square. Let's pick a couple of perfect squares here. Let's pick 4 and 9. Okay, for x equals 2, well, y is just equal to 2. Well, this is square root of 2, or when we graph this for graphing purposes, square root of 2 is about, it's just 1.4. Remember, we're just roughly graphing these. 4, for the regular function, x is 4, y is 4. This one, square root of 4, and that's equal to 2. 9 and 9, and you get the idea. Square root of 9 equals 3. For this bunch, this is where f of x is greater than 1. And what happens? Y equals the square root of f of x is below the graph of y equals f of x. Okay, so hopefully this is a good explainer. I'm going to zoom out a little bit. Oops. Okay, so whole reason for doing this is to explain that chart I talked through. So hopefully this gives you some good numerical examples of how the square root of the function behaves. So let's go back to our page here. And let's do an example. Example 1, compare graphs of a linear function and the square root of the function. So given f of x equals 2x minus 4, graph the functions y equals f of x and y equals square root of f of x on the same grid. So we are graphing this one right here. And then we'll do it in blue. We are graphing, folks, square root of f of x equals square root of 2x minus 4. All right, so let's take a look. First, the linear function. Y equals, or x equals 0, y equals negative 4. And then these, we all know how to graph a line, so negative 2, 2 and 0, 2.5 and 1, 4 and 4, 6 and 8, 8 and 12, and 10 and 16. So for y equals f of x, well, I have x equals 0. Here's the trick here is this part, the radicand, 2x minus 4, we know that has to be greater than 0. So if I solve for x, that's 2x is greater than or equal to 4, x must be greater than or equal to 2, so that I have real number answers. So that's my domain. So when I have an x value of 0, well, it's less than 2, right? So it doesn't fit the domain, so this is undefined. Likewise with 1. When x equals 1, so when x equals 1, so if I do it over here, that's 2 minus 4, I get square root of negative 2. So this is also undefined. How about when x is 2? When x is 2, 2 times 2 is 4, 4 minus 4 is 0, and I have 0, right? And I'm going to star this point because that is my first invariant. So invariant. 2.5, I have 1. If I put in 2.5, so square root of 2 times 2.5 minus 4, and that is square root of 5 minus 4, and that is square root of 1, that's 1. This is my other invariant point. Remember we said the invariant points occur where y is equal to 0 and y is equal to 1. So I'm going to highlight that because those are special points here. Okay, so 2 invariant points. Let's keep going. So 4 and 4. If I think about this y value of 4, if I take the square root of 4, that is just 2. Let's take a shortcut here. 8, what's the square root of 8? Well, that's roughly 2.8. What's the square root of 12? Well, that's roughly 3.5. What's the square root of, oops, oh man, that's a mistake right here. That's not 10. That is 16, folks. Okay, so next one, square root of 16, well, that is just 4. Okay, so let me clean a little bit of this up here. And let's graph this. So first I'm going to graph the red line, which is y equals f of x. So 0, 1, 2, 3, -4, 1, -2, 2, 0, 2.51, 1, 2, 2.51, that's my invariant point. 4, 4, 4, 4, 6, 8, 6, 4, 5, 6, 7, 8, 8, 12, 6, 7, 8, 9, 8, 6, 7, 8, and 12. Let's see, 8, 9, 10, 11, 12. Okay, and I'll just stop there, running out of room. All right, so let's draw a line connecting these. Okay, there we are, and let me just color that in as red, and that's our first line. All right, and then in blue, let me do the square root. I have the first 2 points are undefined at 2, 0. Right there, invariant point, 2.5 and 1. So right about there. 4 and 2, 1, 2, 3, 4 and 2. Right about there. 6 and 2.8, 1, 2, 3, 4, 5, 6 and 2.8, right about there. And 8 and 3.5. 6, 7, 8, and 3.5, roughly right about there. Okay, so when I draw this in, let me zoom in so you can see where the graphs overlap. And this very subtle, this part right here. Okay, and then I'm zoomed in here because I just want to bring your attention to this part here. This is between 1 and 0. So where and we said that this is the point where the graph of f of x is above the graph of, so the graph of square root of f of x is above the graph of f of x, and you can see it visually happening there. All right, and then the other key parts here, these are my invariant points. All right, let's keep going. Next page. Let's answer some questions about the two graphs. Okay, state the domain and range of each function and any invariant point. So y equals f of x. The domain is x such that x is an element of all real numbers. So that's typical for a linear function. And y such that y is an element of all real numbers. What about for y equals square root of f of x? Well, that one, the domain is x such that x is, start from the endpoint, which is 2, greater than or equal to 2. X is an element of all real numbers. And the range, y such that, well, we're starting from 0. Y is greater than or equal to 0. Y is an element of all real numbers. So if I go back to the graph, folks, visually, we can see that x is greater than or equal to 2 for our domain, and y is greater than or equal to 0 for our range. Also, I can just, one moment here, just show you, also makes sense because if I have y equals square root of 2x minus 4, remember this radicand 2x minus 4 must be greater than or equal to 0 to have real values. So 2x is greater than or equal to 4, x is greater than or equal to 2. That's my domain, folks. That's where I get it from. Last part here, invariant points at 2, 0, and 2.5 and 1. Letter C, for which values of x is the graph of y equals square root of 2x minus 4 above the graph of y, f of x equals 2x minus 4? How are these values related to the invariant points? Okay, so if you go back to our chart, so if you go back to our graph, for x greater than 2 but less than 2.5, so x greater than 2 but less than 2.5, the graph of y equals square root of 2x minus 4 is above f of x equals 2x minus 4. How are these related to the invariant points? X equals 2 and x equals 2.5 are the x values of the invariant points, which are 2, 0 and 2.5, 1. D, for which values of x is the graph of y equals square root of 2x minus 4 below the graph of f of x equals 2x minus 4? For x greater than 2.5, the graph of y equals square root of 2x minus 4 is below the graph of f of x equals 2x minus 4. Okay, folks, over on Desmos, we're going to analyze the function and the square root of the function. So this is the example one where we have a linear function, y equals 2x minus 4, and then we graph the square root of that function. Okay, and we had our table of values. I'm going to turn on these points and then zoom in. So you can see right here and right here, those are my two invariant points. And we said between the two invariant points, the square root of the function in blue is above the base function, which is in red. When it's above the invariant point 1, where y equals 1, the base function is above the square root of the function. Let me turn on all these points, and right here and here, those are our two invariant points, key points. The next point, remember I made a point about when you select your values, select something that will have perfect square. So here's a perfect square, 4, 4 on the linear function. Well, we expect this to be 4, 2. The square root of 4 is 2. If I keep going here, so I have my two invariant points. I have 4, 4, 4, 2. Well, here, 6.5 and 9 on the linear function, I should expect 6.5 and 3 on the square root of the function. Let's keep zooming out. Last one I'll show you. You get the point here. Here's our two invariant points. 4, 4 is 4, 2 on the square root of the function. 6.59 is 6.53 on the square root of the function. 10, 16 should be 10, 4 on the square root of the function. And there it is. Example 2. Compare the domain and ranges of y equals f of x and y equals square root of f of x. Identify and compare the domains and ranges of the functions y equals x squared plus x minus 6 and y equals square root of x squared plus x minus 6. Let's analyze this graphically. When I graph this, let's put a couple of key points down here. So in red, I have -3, +2, and then I have y-intercept of -6. This is my graph of y1 equals x squared plus x minus 6. So no surprise here, this is our classic quadratic equation, quadratic function. All right, and then when I graph the square root of it, well, what happens? This is what happens. And so this is y2 equals square root of x squared plus x minus 6. Okay, let's do some comparisons here. For y equals x squared plus x minus 6, what are the x-intercepts? So if we factor that, solve for 0, I have -3 and +2. For the square root of the function, it's still -3 and +2. So right there. What's the y-intercept of the function without the square root? So -6. The y-intercept for the square root of the function, there is none. How about the maximum value? Maximum value of our quadratic function? None. Likewise, none with the square root. What's the minimum value of our quadratic function? That's -6.25. And then with our square root of the quadratic, minimum function is just 0. And in case you're wondering, the window I use, -10, 10, and 1. And then y values, -10, so standard window here, 10 and 1. Okay, example 3. Graph the square root of a function from the graph of a function. Given the graph of y equals f of x, sketch the graph of y equals square root of f of x on the same grid. So number 1, solution. How do we do this? Create a table of values. Consider the invariant point of the function, add these to the table. Locate any key points f of x that are greater than y equals 1 and add these to the table. Number 3, complete the third column of the table taking the square root of the y values. Number 2, on the same grid as y equals f of x, plot the invariant points. Draw a smooth curve between the invariant points. The curve will be above the graph of f of x. Plot square root of y for the key points you identified in your table of values and draw a smooth curve between these points. These will be below the graph of f of x. There should be no points plotted below the x-axis. Okay, let's give this a try. Okay, so let's start with, I'm going to do this, folks. I'm going to label these points A through F. So let me start with this table down here. First, let me, x is -8. Oops, and then one more here. Okay, and then for the function itself, so these are what I plotted. So let's start with this. So I'm going to pull off the key points on the graph, and then I'm going to compare the square root of the functions. Okay, so this is A through F, so this is A, B, C, D, E, F, G, H, and I, all the way up to I. So point A is at 1, 2, 3, 4, 5, 6, 7, 8, -8, 4. So that's point A. Point B is our first invariant point. So that is at -6.5 and 1. So 1, 2, 3, 4, 5, 6.5 and 1. That's B. C is another invariant point. D, another invariant point. E, another invariant point. F, all the way up here, the maximum, actually no, not the maximum, but F all the way up here, that is at -3, 9. G is the y-intercept right here, so this is point F, this is point G. Point H, right there. Point I, and so on. So those are the key points that I need. Okay, and then let me, point A is -8, 4. Point B is -6.5 and 1. Point C is -6, 0. Point D is -3.8. Point E is -3.7, 0. Oops, -3.7 and 1. F is -3, 9. G is 0, 5.5. H is 1, 4. I is 2, 3. All right, so part of it is consider the invariant points. So we got all the invariant points, and I'm going to highlight these. These are the key ones to have. There's my invariant points, and then I selected some other values, that are key points on the function themselves. So when I look at the square root of y, let's just fill these in. Square root of y, this is 2. Square root of y, this is 1. Square root of y, this is 0. 0, 1. Square root of 9, that's 3. Square root of 5.5, that's roughly 2.3. Square root of 4 is 2. Square root of 3 is about 1.7. So roughly. Remember, we're graph sketching here. Okay, and then let's plot point A. We can plot this in a number of ways, right? We can plot this by just looking at these points and plotting them just like we know that this will work, right? But let's plot it in a visual way. If I have point A here at -8 and 4, so x, y, I know I need x. I know I need x square root of y. Well, that's -8, 2. So that's the first one. So this is -8 square root of 4, or -8, 2. So this is what I mean by graphing it visually. At B, I have -6.5 and 1. That's an invariant point, so I know it'll be right here. And then also at this point at C, invariant point, and between B and C, I know that the graph of f of x, so I know that the graph of the square root of f of x has to be above, so I can sketch the graph in like this. Okay, between C and D, since all of this is negative, all of this, there's a discontinuity. So I'm not going to graph any part for square root of f of x. Okay, so I'm just going to make a note here. There is a discontinuity in y equals square root of f of x between points C and D. Okay, because we're not considering taking square roots of, so if y equals -2, well, the square root of y equals square root of -2. Well, that's non-real answers, right? Non-real. That's why there's a discontinuity. All right, let's keep going. Let's sketch the rest of this visually. If I have -3, 9, then the corresponding point on the square root of that is -3 square root of 9. So -3 square root of 9 would be right here. Point D, this is a invariant point. Point E, that's an invariant point. So very subtly, the blue graph is going to be above. and then it kind of curves up to that point. All right. Point G, 0, 5.5. We said the square root of 5.5 is 2.3, so it's 0, 2.3, right about there. 1, 4, 1, 2, 1, 2. 2, 3, 2 square root of 3. So 2, 1.7, roughly, right about there. And then this part, it's all constant. So if I keep plotting points, it's going to be level all the way through. Okay, so when I sketched all of this in, nice curve like this, and then there's an inflection here where it straightens out, and that's it. Okay, so a couple of tips here for ease of graphing. Look for your invariant points first. Okay, and then remember that square root of f of x, the graph, is above the f of x between the invariant points. Okay, remember that. That will also help you. What else? Look for f of x values that are perfect squares. Why? Because something like square root of 9, that's 3. That's easy to graph. Square root of 4, that's 2. So look for values that are perfect squares so that when you graph the square root of those, it's easy to sketch. All right, challenge. How about a bit of a challenge? Example 4. So let's think about this from a transformation standpoint. If negative 16.8 is a point on the graph of the function y equals f of x, identify the image point on the graph of each of the following functions. So let's think about this. So I have y equals f of x. The image point is xy. And I transform that to y equals negative f of 2x plus 10. Well, what am I transforming that into? Well, what's my a value? A value is negative 1. What's my b value? B value is 2. H is 0, and k is positive 10. So when I plug this into my transformation model, x over b plus h x over b plus h ay plus k, well, what does that turn into? X over 2 plus 0, and that's negative ay, and then y is square root of y plus 10. Okay, so if I have x, y, if I have x, y as negative 16.8, and my transformation is x over 2 comma negative square root of y plus 10, then that is negative 16 over 2, comma, negative square root of 8 plus 10. And so that is negative 8 and negative 8. Let's reduce that to negative square root of 2, negative 2 square root of 2 plus 10. So that is my new point right here. Letter B, y equals negative 3 times the square root of f of negative x minus 5 minus 4, all under that same radical, and then plus 2 on the outside. This one's a little tricky, but let's do this. Start with just this part. Start with y equals f y equals f of negative x minus 5 minus 4. With this one, so I'm going to go from the inside to the outside. Let's start with that first. What are the transformations that are occurring here? I have a value is 1, b value is negative 1, h is 5, k is negative 4. So the transformation that's occurring is xy to negative x plus 5, comma, y minus 4. So if I take this transformation, right, remember I'm trying to come up with a function where, or mapping, where I can find the image point for negative 16, 8. So now, if I start with this, let me throw a square root sign over all of it. Like this. Okay, so when I do that, what happens to my mapping? My mapping, negative x, my negative x plus 5. So this one, what happens? Now I'm throwing a square root sign over the entire thing. And then let's keep going. Let's work back to this original, this entire thing. Okay, so let's work back to that. So I've put the square root sign back on. Let's put that negative 3 back on. Well, what happens? Now I'm going to put the negative 3 back on. And then what does that do to my mapping? Negative x plus 5, negative 3 times square root of y minus 4. Okay, last part here. Let's put this plus 2 back on. Okay, so I'm going to rewrite all this. Oops. And then I'm going to put that plus 2 back on. So what happens? That's negative x plus 5, comma, negative 3 y minus 4, and then I'm going to put that plus 2 back on. Okay, so what does my mapping look like? So it goes from xy to negative x plus 5, negative 3, square root of y minus 4, plus 2. So I have negative 16, 8, mapped to negative 16, plus 5, negative 3. Y is 8 minus 4, plus 2. So that's 16 plus 5, that's 21, comma, negative 3, times 8 minus 4 is 4, square root of 4 is 2, that's negative 6, plus 2, that's negative 4. So 21, negative 4. That's the new image point.